Alright guys, we're going to talk about arc length and surface area today. So as far as the arc length formula goes, we'll derive this in class, but if you miss class, we have a pretty basic formula. It's the square root of 1 plus f prime of x quantity squared. The square doesn't go with the 1, and it's not outside the square root. So you find your f prime of x, you square it. It really comes from the distance formula. So it's kind of hard to see why it is that way, but you can see the square root, you can see something about plus and something squared. So it comes from the distance formula, which is how we get the arc length formula. But once you have it, it's incredibly easy to apply. So they'll generally give you an interval from -1 to 5, and then we've got a square root of 1 plus, that's my y, so f prime of x equals 2x minus 3. So a 2x minus 3 squared dx. Very rarely will you actually be able to do this integral. Usually you're just going to have to type this into your calculator and get a decimal. Round it off to 3 places, and that's it. Now, as far as the surface area goes, our surface area formula is a more complicated looking formula, but what you have is really the shell method. So what you want to envision is you've got some sort of a function here, and you want to revolve it about an axis, and so we end up getting this kind of mirrored image out here on the other side. But we just want the surface area. So if you look at each individual little chunk of this, each little piece of arc length, and revolve that arc length around, you end up just getting your surface area. So we're going to take this little chunk here and revolve it around. So you want to think of it more as the shell method, because you're going to be getting these little shells coming around here. You got this piece, you're going to revolve it around. You got this piece, you're going to revolve it around. So we end up basically doing the shell method sideways. And so our formula for the adding up all these little areas is really going to be like the shell method. It's circumference, 2 pi r times, and since it's sideways, the height is that little piece of our arc length. So this is our arc length formula. And this is our circumference. So it's circumference times arc length. Now, if you want to be in terms of y, if you want to revolve it around the y-axis, or anything else, I mean, everything in terms of y is basically going to be very similar. You're going to have 2 pi, the integral of your radius in terms of y, which is going to be the hard part, but then your arc length is going to be the same regardless of if you're revolving it around the x or the y-axis. Your arc length, and actually if you're going to be revolving around the y-axis, the radius of y is even easier, because if I want to go around the y-axis, I just have to figure out how far I am from the y-axis, which is just x minus the axis, just like you do in the shell method. So it's a radius, but you don't really want to do it in terms of y, like I said there a second ago. You really want to think of it in terms of how far from the y-axis are we, or how far are we from that vertical axis are we. It's going to be x minus the axis, or, like in the shell method, the axis minus our x times our arc length. So f1 plus f prime of x squared. So the arc length doesn't change regardless of if you're in terms of x or y. So if I want everything to be revolving in terms of y, I can keep everything in terms of x, which is kind of nice. So this is a much more difficult problem than the arc length is, but you're really using the arc length formula. So let's see what we got here. We want to revolve this fun thing on this interval about the x-axis and about the line y equals 3. So what I'm going to do is draw a quick picture for this just to kind of visualize it. And if I want to graph it really easy, take out your GCF. So I've got zeros at 0 and at 2. And then it's positive, so it opens up. On the interval from 1 to 3, so from here to here, about the x-axis and about the line y equals 3. Okay, so we need our 2 pi. And then our radius is just going to be our, well, we kind of have two different parts here. And we want our radius to be, I'm back up here. We've got a wrong picture, don't we? I've got it at 0 and at -2. I was starting to wonder what we would have to be doing about that at the middle point. So we got our picture off a little bit. So we got it at -2. So we still have this right, but we have it shifted in the wrong direction. All right, that's kind of nice because other words, we're going to have to worry about splitting that. And I'd rather not split it. So if we got it at 1 and at 3, all right, there we go. So our graph here is going to be way up above these 2 points. So we're looking here and here. Okay, that's a little bit better. So 2 pi, and then we want to revolve it around the x-axis. So we're going this way. So we end up with this way down here somewhere. So revolving it this way. So our radius is from our function down to the ground here, down to 0. So our function is just our x squared plus 2x. That's our radius from there to the axis. And then times our arc length. So 1 plus f prime of x, 2x plus 2 squared dx. And we import our bounds from the problem itself, 1 to 3. So that's our x-axis. And then if I want to go about the line y equals -3, the only thing that's going to change, not our arc length, is really going to be our radius. So 2 pi, and we roll from 1 to 3. This radius from the function all the way down to the axis would be our x squared plus 2x minus our axis, which is in this case -3, so plus 3. And then the square root of the exact same thing. Now again, these are not things that you're going to be able to do by hand because the square root's really going to mess you up. I mean, there's a couple that you might be able to do a u substitution, but not generally. All right, I'm going to end the recording now and start a new one for revolving about the y-axis and some vertical lines.